Every year, you celebrate a day where light and dark are supposedly, flawlessly equal.
Right.
Like you've been taught it since grade school. You pictured this perfectly straight line drawn right down the middle of the globe.
Yeah, exactly 12 hours of day, 12 hours at night.
But astronomical data proves that you have essentially been living a lie.
A very persistent lie.
Right. And the real story behind this day involves, well, optical illusions, a 16th century religious crisis.
Which is wild.
It is. And the actual reason your Wi-Fi randomly drops out in late March.
The misconception is so deeply ingrained that it is literally baked into the word we use to describe it.
Welcome to today's deep dive. We are taking a massive stack of sources, everything from celestial coordinate definitions to historical papal decrees and even satellite telemetry.
A lot of data.
A ton of data. And we're looking at a calendar event you've lived through every single year of your life, but probably completely misunderstand, which is the equinox. Our mission today is to uncover the mind-bending reality behind it. We're going to show you how a simple, first day of spring is actually a profound physical alignment of our entire solar system.
And it really is profound when you look at the mechanics.
Okay, let's unpack this. Because the sources we're looking at today are just packed with facts that completely shatter the conventional wisdom of what an equinox actually is.
We really have to start with the name itself, I think, because it promises something the universe simply does not deliver.
Right.
If we look at the etymology, equinox is derived directly from Latin. You have equa, which means equal, and nox, which means night.
Equal night.
Equal night. The name implies this universal, perfect 50-50 split of daylight and darkness.
Like 12 hours of sun, 12 hours of pitch black, no matter where you are on the planet.
That is the promise. But the astronomical data reveals a bombshell, honestly. On the day of the equinox, day and night are absolutely not equal.
Not at all.
No. If you are standing directly on the equator on the equinox, your daylight is actually about 14 minutes longer than your nighttime.
Wait, 14 minutes?
Yep, 14 minutes of extra daylight. And that discrepancy gets even larger the further north or south you move toward the poles.
Wait, if the sun is hovering dead center over the equator, shouldn't it be an exact 12-hour split? I mean, I always pictured the equinox like a laser pointer hitting a globe.
Okay, yeah.
Like if you shine that laser perfectly at the middle of the sphere, the light naturally stops exactly at the halfway mark, right? Leaving the other half in complete shadow.
The laser pointer visualization makes intuitive sense, but it highlights the first major flaw in our thinking.
Okay.
Because the sun is not a single, infinitely small point of light.
Right.
From our perspective on Earth, the sun is a giant disk in the sky. And sunrise isn't defined by when the exact center of that disk hits the horizon.
Oh, is it when it first touches?
Yes. It is defined by when the very top edge, what astronomers call the upper limb, first becomes visible.
Oh, I see. So because the sun has like a physical width, that upper edge peaks over the horizon before the center does.
Exactly.
And it lingers after the center has already set. So it's less like a laser pointer and more like, I don't know, a wide flashlight beam spreading out over the curve of the Earth.
That's a great way to put it. That sheer physical size is giving us bonus daylight.
Bonus daylight. Wow.
Put those two factors together, and the math of an equal night completely falls apart. But the physical size of the sun is only half the culprit here.
Oh, there's more.
Yeah, the other half is the air you are breathing right now. Earth's atmosphere physically bends or refracts sunlight.
Refracts it. Okay.
Because of this refraction, the atmosphere acts like a giant invisible lens. It essentially lofts the sun's image higher in the sky than it actually is in reality.
Wait, so we are seeing the sun before it has actually risen above the physical horizon?
Yes. To give you the exact numbers from the astronomical almanacs, standard atmospheric refraction bends light by about 34 arc minutes. Combine that with the radius of the sun's disk, which is about 16 arc minutes.
Hold on, arc minutes.
Oh, right.
For those of us without astronomy degrees, how big of a slice of the sky are we actually talking about here?
Fair question. Imagine the sky above you as a giant 360-degree dome.
Okay, I'm picturing it.
One single degree of that dome is roughly the width of your pinky finger held out at arm's length.
Oh, wow, that's tiny.
It is, and an arc minute is just 1/60th of that tiny pinky width.
1/60th of a pinky. Okay.
It sounds minuscule, but in orbital mechanics, it changes everything. Because of that atmospheric bending and the sun's radius, you get a total shift of 50 arc minutes.
Right.
This means that when you are looking at the top edge of the sun sitting right on the horizon line, the actual physical center of the sun is 50 arc minutes below the geometric horizon.
That is wild. So the next time I'm at the beach watching this, like, beautiful sunset, the sun I'm looking at is technically already gone.
It's technically gone, yeah.
Yeah. It's just a mirage projected over the horizon by the atmosphere. That just completely breaks my brain.
It is a literal optical illusion. Our atmosphere bends the light around the curvature of the Earth to give us extra daylight.
Huh.
And because of this illusion, the real day of perfectly equal light and dark doesn't happen on the equinox at all.
Well, then when does it happen?
Depending on your latitude, it happens a few days before the spring equinox and a few days after the fall equinox.
Okay.
Astronomers actually even have a separate word for this day of true equality. They call it the equilux.
Equilux. Equal light.
Exactly. Equal light.
Okay, so if the equinox isn't actually about equal light, what is physically happening to our planet on this specific day? Like, what is the actual definition then?
The true official definition of an equinox is a singular moment in time. It is the exact instant when the plane of Earth's equator passes flawlessly through the geometric center of the sun's disk.
Just that one exact second?
It's that second. At this specific moment, Earth's rotational axis is tilting neither toward nor away from the sun. It is perfectly perpendicular to the incoming solar rays.
Which means the solar terminator, the shadow line dividing day and night on the globe, runs straight from the North Pole to the South Pole.
It cuts the planet vertically, exactly perpendicular to the equator.
Right. And looking at the sources, this creates some completely bizarre phenomena at the extreme ends of the Earth.
Oh, it really does.
Because of that atmospheric refraction lens we just talked about, around the time of the equinox, the sun doesn't just rise and set at the poles. It basically just rolls sideways along the horizon.
It's an incredible sight.
There was this really incredible piece of data in our stack from 2021. For a brief window of about 4 days around the equinox, both the North Pole and the South Pole experienced daylight simultaneously.
I mean, let the geometry of that sink in for a minute.
It's crazy.
The poles are the absolute opposite extremes of the Earth. They spend 6 months in total darkness and 6 months in constant light. And yet, for a few days, the atmosphere bends the solar rays just enough that an observer standing at the North Pole and an observer at the South Pole could both look out and see the sun at the exact same time.
Just because the air is bending the light?
Exactly.
But even with that incredible alignment, the celestial clockwork isn't, like, completely symmetrical, is it? We have this assumption that the seasons are all exactly the same length, but the Earth's orbit has a pretty big quirk.
A major quirk. Johannes Kepler figured out the laws of planetary motion centuries ago, proving that planets don't orbit in perfect circles.
They're ellipses.
Right, they orbit in ellipses. So the Earth's orbit around the sun is slightly oval-shaped. Sometimes Earth is closer to the sun, and sometimes is farther away.
And how does that actually affect the length of the seasons?
This is where Kepler's laws get really interesting. Think of it like a gravitational slingshot.
Okay.
When Earth is closer to the massive gravitational pull of the sun, it gets whipped around faster in its orbit.
Makes sense.
But when it's farther away, the gravitational pull is slightly weaker, so it moves slower.
So our speed through space is constantly changing.
Drastically changing. And because of this changing speed, the interval from the March equinox to the September equinox, when Earth happens to be farther away and moving slower, is about 186 days.
Okay.
But the interval from the September equinox back to the March equinox, when we are closer and moving faster, is only about 179 days.
Wait, 186 days for one half of the orbit and 179 days for the other half?
Yeah.
That's a 7-day difference?
It is.
Which means the North Pole gets a full extra week of polar daylight compared to the South Pole? That's so unfair.
The mechanics of the cosmos are incredibly precise, but they are absolutely full of these asymmetrical quirks.
Which brings up a really fascinating problem.
Oh, the calendars.
Yeah, the calendars. If the math of the solar system is this complex, with elliptical orbits and optical illusions and changing speeds, how did human beings ever keep track of it?
Mostly, we didn't.
Because reading through the historical records in our sources, it seems like we were absolutely terrible at it, and it caused a massive global crisis.
It caused a crisis that literally broke our calendars.
Wow.
To understand how astronomy collided head-on with human history, we kind of have to rewind all the way to 45 BC.
Okay, let's go.
Julius Caesar establishes the Julian calendar, and he officially locks in the date of the spring equinox as March 25th.
I mean, pick a date on the calendar, declare the start of spring, and move on. Makes sense for the time.
It makes sense until you do the math. The Julian calendar year was about 11.3 minutes longer than the actual physical tropical year.
The tropical year?
Yeah, the tropical year is just the exact time it takes for the Earth to complete one full cycle of seasons.
Honestly, 11.3 minutes does not sound like a big deal.
In a single year, it isn't. Think of it like a wristwatch that loses exactly 1 second every single day.
Okay.
For the first few weeks, you don't even notice. But after a few years, your watch is so far behind that you are showing up completely late for work.
Right. Over the centuries, that 11.3-minute annual error just compounded. It meant the human calendar was drifting out of sync with the actual solar system by about one full day every 128 years.
Oh, wow.
Yeah, fast forward to the year 300 AD, and the equinox drifted from March 25th back to March 21st.
Oh, I see where this is going.
Keep going to the 1580s, and the physical equinox was actually happening on March 11th.
So the calendar hanging on your wall says it's late winter, but the actual planet is already well into spring.
Exactly.
But why did anyone in the 1580s actually care enough to fix it? I mean, life was pretty agrarian anyway.
The catalyst was Easter.
Ah.
In the Christian tradition, the date of Easter is intrinsically tied to the spring equinox. The Council of Nicaea in 325 AD had anchored Easter to the vernal equinox, assuming it would always fall around March 21st.
Okay, but it kept moving.
Right. By the late 1500s, because of that invisible calendar drift, Easter was marching ever closer to the summer months. The church was literally losing its grip on the seasons. It was like a slow-motion Y2K bug for the 16th century. The calendar was essentially lying to them.
That's exactly what it was.
So Pope Gregory III steps in, and he establishes the modern Gregorian calendar to stop the drift. And his fix wasn't just resetting the date, right? It was changing the actual math of leap years.
It was a brilliant mathematical correction, honestly. Under the old system, every 4 years was a leap year, no matter what.
Right, which was adding too much time.
Exactly. Pope Gregory realized that added too many days over the long run. So he instituted a new rule.
Yeah.
You still have a leap year every 4 years, unless the year ends in 00.
Wait, so century years?
Yes. Century years, years like 1700, 1800, and 1900 would no longer be leap years.
But wait, the year 2000 was a leap year. I remember that.
Right, because that is the final piece of his rule. A century year is skipped unless it is divisible by 400.
Oh.
So 1600 and 2000 kept their leap days.
That is surprisingly elegant.
It really is. By implementing this rule, the Gregorian calendar removes exactly 3 leap days every 400 years. Instead of 100 leap years, you only get 97. That tiny mathematical tweak keeps the human calendar year almost flawlessly aligned with the astronomical year, keeping the equinox hovering right around March 20th or 21st to this day.
It's amazing that it took a papal decree to fix a math error from ancient Rome.
Yeah.
But what really stood out in the sources is that while Europe was, spiraling over a drifting calendar, other cultures were nailing this celestial alignment without any modern technology at all.
Oh, the cultural understanding of the equinox is profound globally.
Yeah.
Look at the architecture of Angkor Wat in Cambodia.
I saw that in the notes. That's incredible.
It was designed so that during the equinox, the sun rises in a flawless line directly over the central highest tower.
Just a perfect alignment.
It's a staggering display of ancient astronomical precision.
And you've got the Persian New Year, Nowruz, which is celebrated by millions of people across Central Asia today. They didn't just arbitrarily pick a random day for their new year. They tied it directly to the exact astronomical moment of the Northern Hemisphere's spring equinox.
Which highlights a major nomenclature problem we actually still deal with today.
What do you mean?
Well, we are so used to calling them the vernal, meaning spring, or autumnal, meaning fall equinoxes.
Right.
But that language is entirely hemisphere biased.
Oh, of course. Because when it's the vernal equinox in New York, it's actually the autumnal equinox in Sydney, Australia.
Exactly.
Calling it the first day of spring is completely confusing for literally half the planet.
The scientific community has really tried to correct this. You'll see alternative terms in the literature like March equinox and September equinox, which is better.
But it still relies on our specific human calendar.
Exactly. The most scientifically precise, universally applicable terms are actually the northward equinox and the southward equinox.
And those refer to what the sun is actually doing in the sky, right?
Right. Yes. The northward equinox in March describes the exact moment the sun's apparent declination crosses the celestial equator moving north.
Okay, apparent declination. Let's translate that. If I'm standing outside, what does that actually mean?
Imagine tracing the sun's path across the sky on a giant invisible glass sphere surrounding the Earth.
Okay, a glass sphere.
Declination is just the astronomy term for latitude on that glass sphere.
Got it.
So a northward equinox simply means the sun's path is crossing the Earth's equator and moving into the northern half of that sphere.
That makes total sense.
And in September, the southward equinox marks it crossing back into the southern half. It describes the physical geometry of the solar system, regardless of where you are standing or what calendar you happen to use.
Northward and southward, it feels much more grounded in physics.
It is.
And if the sun is perfectly aligned with the equator during these exact moments and it's blasting radiation straight at Earth, what happens to all the satellites we've parked right over that exact same equator?
They have a very bad time.
Because reading through the telecom data in our sources, I was totally sidelined by this concept of a sun outage. I mean, I always assumed bad weather knocked out satellite signals, not the literal position of the sun.
Weather plays a role, certainly, but the alignment of the Earth and the sun during an equinox has severe direct consequences for modern telecommunications.
How so?
A sun outage plagues geostationary satellites. These are the satellites that sit in a fixed orbit directly over the Earth's equator. They provide satellite TV, internet, and critical communication links.
So they are sitting exactly where the sun's focus is during the equinox.
Precisely in the crosshairs. Think about the geometry. The sun is passing directly over the Earth's equator. This means that for a few days around the equinox, from the perspective of a ground station dish looking up at its satellite, the sun's going to track directly behind that satellite.
And the sun isn't just a bright light bulb, it's a colossal nuclear reactor blasting out intense radiation across the entire electromagnetic spectrum.
That immense radio frequency energy completely overwhelms the reception circuits of the ground station down on Earth.
Because it's too loud.
Way too loud. The station's antenna is pointing up at the satellite, trying to lock on to a faint data signal, but the sun is roaring right behind it in the exact same line of sight. It's like trying to listen to someone whisper to you while a jet engine is taking off right behind their head.
That's a great analogy.
The solar noise drowns out the signal entirely, causing temporary disruptions, internet drops, and degraded communication links.
So if you're trying to stream a movie in late March or late September and your Wi-Fi randomly drops out for 10 minutes, you might literally be feeling the physical effects of orbital mechanics aligning.
You are experiencing an astronomical event interrupting your router. Yeah.
That's hilarious.
And the satellites themselves suffer during this time, too. Usually because the Earth's axis is tilted, a geostationary satellite sitting over the equator will pass slightly north or south of the Earth's shadow.
Oh, so they're always in the light.
Exactly. They remain bathed in sunlight nearly all the time, which keeps their solar panels fully charged.
But during the equinox, the Earth's tilt is completely perpendicular to the sun.
Which means the Earth casts its shadow directly outward along the equatorial plane. Those geostationary satellites are plunged straight into the darkest part of the Earth's shadow for the absolute longest duration of the entire year.
So they lose their power source.
They lose their solar power completely and have to rely entirely on their onboard backup batteries. It is an incredibly stressful time for satellite power management.
Here's where it gets really interesting, though. If the equinox causes satellite blackouts and battery drain here on Earth, what does it do elsewhere in the solar system?
Oh, man.
Because any planet with a tilted axis is going to have its own equinoxes, right?
Every planet with an axial tilt experiences them. But they play out in drastically different ways depending on the planet's unique characteristics. The most dramatic example in our solar system is, without a doubt, Saturn.
Because of the rings.
Because of the rings. Saturn's axis is tilted, just like Earth's. But it also has this expansive ring system orbiting directly around its equator.
Right.
Normally, sunlight hits those rings from above or below, illuminating the ice and rock, making them brilliantly bright to our telescopes.
But during a Saturnian equinox, the sun is shining completely edge-on to the equator.
It strikes the ring system perfectly edge-on. And you have to understand the scale here. These rings are wider than multiple Earths, but they're incredibly thin. In some places, only a few dozen meters thick.
So when a light hits them from the side,
they practically vanish. They receive almost no direct sunlight.
That's so eerie.
In fact, during this brief window, the rings actually receive more light reflecting off the surface of Saturn itself, we call planet shine, than they do from the sun.
I can't even wrap my head around that. Like a structural feature the size of a planet made of millions of ice chunks just suddenly disappearing into darkness.
It's breathtaking.
And because Saturn takes nearly 30 Earth years to orbit the sun, this isn't an everyday occurrence, is it?
No, a Saturn equinox is a very rare event, happening only once every 14.7 Earth years. We actually had a spacecraft there to witness it, though.
The Cassini probe, right.
Yes, in 2009, Cassini captured the Saturn equinox up close. Because the sun was hitting the rings horizontally, any chunk of ice or moonlit that was slightly taller than the rest of the rings cast massive, elongated shadows.
Like shining a flashlight flat across a dusty floor, suddenly you see every single bump.
Exactly that. It allowed scientists to see three-dimensional structures and towering debris in the rings that are completely invisible during the rest of the Saturnian year.
That is just so cool. And Mars has these intense equinoxes too, doesn't it?
Mars does. Its most recent northern spring equinox was in December 2022, and its northern autumn equinox was in January 2024.
Okay.
But Mars doesn't have a thick atmosphere or stabilizing oceans like we do.
Right, it's a desert.
So its equinoxes drive massive, violent shifts in global atmospheric pressure as carbon dioxide rapidly freezes and thaws at its poles as the sunlight shifts.
It is wild to think about how we started this deep dive.
Yeah. I mean, we started by picturing a clean, orderly 50-50 split of light and dark, drawing a perfectly straight line down the middle of a piece of paper.
The grade school version.
Right. But the reality of the equinox is so much messier and honestly so much more dynamic than that.
It's a highly complex interplay of orbital speed, atmospheric physics, and planetary geometry.
From the optical illusion of extra daylight caused by the air we breathe, to a pope doing fraction math to stop the calendar from ruining Easter.
Yeah.
We've seen how ancient architects built stone temples to perfectly catch this alignment, and how modern telecom engineers have to, over-engineer batteries just to survive its shadow.
Which brings us back to the reality of what this day actually is.
So what does this all mean? It means the equinox isn't just an arbitrary date printed on your wall calendar to tell you when to buy spring clothes.
Definitely not. It is a profound physical event. It is a moment where the vast, grinding mechanics of the cosmos briefly intersect with our daily lives, impacting everything from the history of our civilization to the internet connection in our homes.
It connects us directly to the gears of the universe. And I really want to leave you with one final thought.
Ooh, all right.
We spent time today talking about how Earth's atmosphere bends light. We talked about how 34 arc minutes of refraction creates an optical illusion, making our days artificially longer and allowing the sun to linger on the horizon as a mirage.
Right.
But zoom out from Earth for a second. Look out into the galaxy at the thousands of exoplanets we are discovering.
The truly alien worlds.
The incredibly weird ones. Worlds with atmospheres that are unimaginably thick or made of toxic, swirling metallic clouds.
Oh, wow.
If our relatively thin, transparent atmosphere can bend light to create an equinox illusion, how completely distorted and bizarre might a day look during an equinox on an alien world?
I can't even imagine.
On a planet where the atmosphere bends light so severely that it loops entirely around the planet, the optical illusions would be beyond human comprehension.
That is going to keep me up at night. The idea that a sunrise on another planet's equinox might look like a continuous glowing halo encompassing the entire sky.
It's entirely possible.
Well, thank you for joining us on this deep dive into the equinox. We hope the next time March or September rolls around, you won't just look at your calendar. You'll look at the horizon, you'll think about that bent light and the satellites powering down above you, and you'll realize that perfectly straight line drawn down the middle of the paper is actually beautifully, wonderfully flawed.